This is project 1, video number 3, the one in which I do the documentation and finishing touches. Let's see. I guess the first thing I'll do, you have to have a description of what the function does. So say what the function does here. Make sure you don't write those exact words. You have to write a description of what the function does. For this one, you got to say what the layout of the fixed charges is, where the moving charge starts, the free charge particle, how you get things started, what the program does. Obviously, it creates those 3 graphs, but you got to say what the graphs are. And then I get the by Jeffrey Schnick in there. So I'm working on the documentation. All the comments that are just for human readers start with a %sign. Input variables. So corresponds to the values that are given to the program by the user. When the user goes to use it, you wrote it, but when somebody goes to use it, what they got to put in. And the input variables are m, which is the mass of the free particle. So the mass of the particle, whatever you call it, up there, the mass of the particle that was initially moving, it's an m. And then percent QP equals the charge of the free particle, and percent V0 equals the initial speed of the free particle, which by this time a person knows already that it was launched at along the x-axis. So v0 is the x component of the velocity. Is another thing for another name for the initial speed, but that's the only component there is. So I'm going to call it the initial speed, and then output variables. There are none. Okay, that takes care of saying what the variables are. Attribution. It turns out I didn't have to look up anything on the internet to figure out how to do this. So I'm going to write no outside resources used. If you use the video to write your code, then you should say so. Say which video you used. If you use videos 2, I use video 2 to write the code. Tell a little story here about how you get things done. I use video 2 to write the code. I use video 3 to check my documentation. I did it all on my own, but there were a few things that I fixed based on things that I found in video 3, something like that. So tell me a little story here, and don't just write what I'm writing. I used no outside resources to write this code. Click here. So don't copy my words at that point. Then I should explain any unusual steps here. So is something that is not self-evident. So you try to make your code self-documenting in the sense that I chose the name K for the Coulomb constant, and that's standard in physics, so people expect that to be the case. I think I'll say here, this is the charge in coulombs of one of each of the fixed charged particles. I'm going to try to make this wrap comments. That didn't work for me, so I seem to be going off the page here, so when somebody prints this, it won't all show up. So I'm going to try %, and then let's see if this fits in. X coordinate of charged particle of fixed charged particles. They all have the same x coordinate. Distance x-axis of each fixed charged particle. So it corresponds to particle number 1, but they're all the same distance. I exploited symmetry, as you saw in the pencil and paper part. I'll call this the time step. Then with n being equal to 1, I think it's pretty clear that these are the initial values, and then I think it should be pretty clear what we're doing here. And once again, I used reasonable variable names. QP we've already defined up there. So in physics we tend to use Q for charges, so it should be pretty obvious that this is the Coulomb constant times the charge of one particle times the charge of another particle. And then this x, where it's at along the x-axis, that's pretty clear. x1, we defined it. It was, to me, not that obvious. The mass of the charged particle, so I think what we're doing here is pretty obvious, and the same thing with a plot. So we're not doing anything really, any tricky programming that a person's not going to be able to figure out what's going on. So based on your description saying what the function does here, a person should be able to figure out what's going on along in here, and then in the while loop, and even more so here. So I think I've got it plotted. Let's because I want to make I got it documented. I want to make sure it's still working. So do a Control S, go to the command window. Sometimes you're typing in comments, that shouldn't change anything, but sometimes with a bad keystroke something does change. So I think it was motion graphs. I guess I'm not sure what it was. I'm going to guess that's what it is. And I went mass 0.001 kilograms, charge 5 times 10 to the minus 6, so I'll call it 5 microcoulombs. And then I was using, that's the one value I do remember, 100. So there's no such thing as motion graphs. So let's see what I got here. See what the actual name of it is. Oh, motion graphs. So I'm probably in the wrong directory. Let's go back here and see if I can switch to my documents. I got to get into that directory. Spring 132 projects, project 1, my code. Let's try that again. seems to be running, and it looks like it's running correctly. It looks like with the charge and mass I picked, it doesn't come back, or it comes back, even though I launched it at a pretty high speed. But yeah, velocity goes to 0, acceleration goes to 0 when it. No, the acceleration is always negative, so this one comes back. Go try a higher speed. Make sure it still goes through. Let's try 1,000 meters per second. Launch speed goes right through. Yeah, everything looks like it's still working. Alright, so going back to the edit window, I gotta title the graphs. I'm going to try title single quotes. The title goes inside the parentheses of the title function, and it goes in single quotes. And this first graph is X, call it position versus time. And then for the x-axis, I'm going to call that X. No, T. I made that mistake before. And Y label. That's X. I should tell what units it's in. That's in meters. And T, use square brackets to say what the units are. So that's in seconds. Don't use parentheses. That then makes it look like you got time as a function of something called S. Put it in square brackets. So X label, Y label. Let's see if that works. Control S and run it. So up arrow to make that come back. Run it, and it says position versus time, and then X in meters versus T in seconds, which goes up to 3 times 10 to the minus 4th seconds. I think that's good. So I got to do some more editing. Let's get the editor up there. And I'll close the graph window. Alright, so I'm going to try copying all 3 of those things after that plot and after this plot. Then the second one, I'm actually graphing velocity. It's really the component of the velocity in the x direction, which is all there is. So it's the magnitude of the velocity as well, versus time. So t is good, and then that's v in meters per second. And then acceleration versus time. And t is still good, and that's a in meters per second to the 2. Control S to save it. Run it. I'm going to go up arrow, run it, see what we got here. Position versus time, velocity versus time, acceleration versus time. There it is, position versus x versus t, v in meters per second, square brackets, not parentheses, versus t in seconds, and a in meters per second squared versus t in seconds. So yeah, this is looking good. So I think the code is actually right still. Incomplete now that I've put the window dressing on the graphs. So at this point, it's time to go through the grading checklist that was provided with the handout. So let's see if I got things covered. The pencil and paper part must have each of these parts, a complete algebraic solution. I checked this, and including relevant diagrams, and there has to be at least one diagram. I think I had 2 for each function and outline of the steps the program will execute. I had that, and I used that in writing the code. So they call that pseudocode, just stating in partly plain English, partly statement functions from whatever language. Any way you can communicate what the program has to do, get that down there, write your pseudocode first, and then use that to write the actual code. And then for the program part, 1 point for a reasonable attempt at writing the program. I think I nailed that. Note that your program must consist of one or more .m files. Mine is exactly one .m file, so that's cool. 1 point for a program that works properly. Mine works properly as of now. I hope I don't mess it up before I turn it in. I gotta make sure it doesn't print anything to the screen if they use a semicolon at the end of the statement. Am I there on that? I had it printing stuff to the screen earlier. Yeah, it prints nothing to the screen. It does create some graphs, but what I mean there, what is meant there is, for instance, if somebody leaves off the semicolon right there, then I've saved that. Then if they go to run it, even with the semicolon out there, it prints out the value of m, that line that had an assignment statement and that didn't end in a semicolon. So very useful for troubleshooting purposes, but it's stipulated that to get the credit for the program working properly, it cannot print stuff to the screen. So you gotta, if it's printing stuff to the screen, you gotta fix that. And in this case, it's just a matter of putting that semicolon in there. So mine does generate the graphs. They're in the right order, top to bottom. X versus T, V versus T, and A versus T. That was stipulated in a separate email message. I guess I got to make sure. I think I may have checked this before, but make sure I got that. I go MQV for the order of the arguments. Write a MATLAB function that takes 3 arguments. I've got exactly 3, namely mass, charge, initial speed, in that order, perfect, and produces a graph of position versus time, V sub x versus time, A sub x versus time, for that time interval while it's between 0 and 20 centimeters. Got that, and it was stipulated in that other email message that you have to do it in the order provided from top to bottom on one page. All those graphs on one page. That's why I had to use subplot. If it hadn't said it has to all be on one page, I think there's a way of using plot over and over against where you get each one on a different page. But that was not allowed. So to get this point, your program must correctly do what it's supposed to do, and as long as the user puts a semicolon, doesn't matter in this case whether there's a semicolon or not. Sometimes it does. If the function returns something, it's going to print out the value of that something when you run it, unless you put a semicolon, and then it won't. But we're getting nothing printed. So I think we're cool as far as program works properly. 1 point for documentation and final touches. Let's see, you must have your name in every .m file. Yeah, I was afraid I was going to forget that, but I got it covered. Code must be documented for each function. This will include a comment starting on the first line after the function statement. Okay, here's the function statement. The next line after that is this. This is the first line after the function statement. I didn't really do it. So I reserve space where you have to do it. Say what the function does here. You know, for the case of fixed set of charges on a Cartesian coordinate system with all of them at the same distance along the x-axis, etc., etc., etc. Describe the situation, say what the function does. You have to do it right there, starting on the first line after the function statement. No space, no nothing, first line. Another set of comments providing a list of arguments of the function, the input variables, with beside each argument a statement of what that variable is. So I got that. Should do the same thing for the output variables. I don't think it. Oh, here it is. For the case of a function that returns one or more values, comments must be included that provide a list of the returned variables and state what each variable is. So I got that list even though there is none. It's not really a list, it's just a statement that there are no output variables, so nothing gets returned by motion graphs, the function. For the case of a function that includes segments that are not self-explanatory, so I checked that out. I felt that I made them self-explanatory in large part by choosing variable names that people that would tell the reader what the variable represented using typical physics notation. The purpose of those statements. So I didn't feel that I had to put down too much in the way of explanation, but this Q1 business, make sure that that's not like the charge of, they don't think that's the charge of the free particle. So this is the charge in coulombs of each of the fixed charge particles. So I felt I had to explain what a couple of the variables that were used within the function were. Explain the purpose of those. Then you must provide attribution, include a comment giving attribution to whatever research. In particular, if you watch the video, make sure you read about that. So you don't get any credit for the whole documentation scheme if you just copy my statement. So if you actually did it all on your own, and then you looked at my videos and found that yours was perfect, you could just write in there. I did it all on my own and just used the videos as a check, making no changes after I looked at them. Or if in the future you do the whole thing and you didn't look at the videos, then there's you could put something, you can mention that you did it all on your own, didn't use any outside resources, but do recommend looking at the videos just to make sure that there's not stuff that you left out. So I would say that we've got it covered. I'll go one more quick check to make sure that it's saved, so that save box is grayed out, and I just want to make sure it's still, like I messed it up on purpose so that I could show you this. Let's make sure I fixed it correctly. I haven't run it since then. And it's not printing anything out to the screen. It's generating the correct graphs. They look good. Just for fun, I'm going to cut that in half. Oops. Up arrow. Edit. 500. Want to see if I can get it to switch over. It's gone all the way through. I know it comes back at the 100, but I don't think I doubt if I have to go that low to make it come back. Yeah, there it is. So it looks like it's going to be pretty close to 200. Like 250 might not come back, but it comes back in this case. Starts at 0, goes away from the origin, and then comes back. So it goes over and then back. Got 0 velocity at the turnaround point, and it's got maximum negative acceleration at the turnaround point. So it got as close as possible and then turned around. Where if it goes through, the acceleration actually goes to 0 for that instant where all the where the moving particle is at the same value of x as the other ones. To me, I only did it with a positive charge. I consider only the positive charge to be realistic. If you put a negatively charged particle on there, it's bound to come off the x-axis. Like with the positively charged particle, positive source charges, if it starts to come off the x-axis, even a really tiny amount, it's going to make it so that it's closer to the charged particles on the side that it came off. They'll be exerting a greater force, and so the net force will push it back toward the, as far as any side-to-side motion, push it back toward the x-axis. Whereas if you put a negatively charged particle on there, then if it comes off because you didn't launch it exactly perfectly straight, starts to come off the x-axis a little bit, that there's going to be positive feedback for that, because now it'll be, again, closer to the fixed charges on the side that it came off, and it's attracted to them. So closer to it means the force is greater, so the net force is going to be toward them, and so it'll veer off the path. And so I would expect that if you actually tried to do the experiment, the one that we got here might be hard to be set up, but it would work. If you did it with a negative charge, it would undoubtedly, the charged particle would undoubtedly veer off, especially at the speeds that I'm talking about here. But I'd say that's a wrap. We've done finishing touches and documentation, and then I went through the grading checklist to make sure that I had everything covered. So that does it for Project 1, Video 3.